For over a century, we've trusted our telescopes to show us the truth about the cosmos. We've built our understanding of dark matter, galaxy evolution, and the structure of the universe on images captured by instruments worth billions of dollars. But here's what makes this disturbing. Every single one of those images is a lie. Not because our instruments are broken, but because space itself is broken, curved and twisted by gravity in ways that fundamentally distort everything we observe. Einstein predicted this cosmic deception in 1915, but it took decades before astronomers realized the full scope of what they were dealing with. When light travels from distant galaxies, it doesn't move in straight lines through empty space as we once believed. Instead, it follows the curves and valleys carved into space-time by massive objects. Curves so severe they can split a single galaxy into multiple images, magnify objects by factors of hundreds, or create perfect rings of light where no ring actually exists. The numbers are staggering. The Hubble Space Telescope has cataloged over 500 strong gravitational lenses, each one representing a cosmic hall of mirrors where reality and illusion become indistinguishable. Some galaxies appear dozens of times larger than they actually are. Others seem to exist in multiple places simultaneously. In extreme cases, we're seeing the same supernova explosion happening multiple times, separated by months or years, as different paths of light finally reach our telescopes. Leading astrophysicist Dr. Sherry Hsu from the Max Planck Institute puts it bluntly: we are never seeing the universe as it actually is. We are always seeing it through the lens of gravity. This isn't speculation. It's been confirmed by missions like the James Webb Space Telescope, which has revealed that gravitational lensing is far more pervasive than we ever imagined. So how can we trust anything we see? How do astronomers separate truth from gravitational fiction? And what does this mean for everything we think we know about the cosmos? Tonight, we're diving into one of astronomy's most mind-bending problems. If the universe is constantly lying to us through gravitational lensing, how can we ever know what's real? The story begins with a simple question that leads to a profound crisis of knowledge. When you look at an image from the Hubble Space Telescope, you're not just seeing a photograph. You're seeing light that has been sculpted by the gravitational fields of countless objects during its journey across billions of years. Every massive galaxy, every dark matter halo, every black hole along the way has left its fingerprint on that light, bending and shaping it in ways both subtle and dramatic. This isn't a minor correction that astronomers can easily account for. In 2019, the Dark Energy Survey identified gravitational lensing effects in over 100 million galaxies. That is not a small sample of unusual objects. That is essentially everything we can see in the distant universe. The implication is staggering. Virtually every observation of the deep cosmos is contaminated by gravitational distortion. But here's where the story becomes truly fascinating. Instead of seeing gravitational lensing as an obstacle to understanding the universe, astronomers have learned to read these distortions like a code. They've developed techniques so sophisticated they can use the lies to uncover deeper truths. By carefully analyzing how light has been bent, they can map dark matter that's completely invisible, weigh galaxies with unprecedented precision, and peer further back in time than ever before possible. We're about to explore 3 revolutionary discoveries that emerged from this crisis of cosmic vision. First, we'll see how gravitational lensing revealed that our entire understanding of matter in the universe was fundamentally wrong, that what we thought was everything is actually less than 5% of reality. Second, we'll discover how astronomers learned to use the universe's own gravity as the ultimate telescope, creating magnifications that no human technology could ever achieve. And finally, we'll confront the philosophical implications of living in a universe where observation itself changes what we observe. If you are fascinated by the hidden mechanics of cosmic observation and the extraordinary methods scientists use to extract truth from deception, subscribe and hit thumbs up. And here's something to consider. If our most basic observations of the universe are fundamentally distorted, what other assumptions about reality might we need to question? Comment below with your thoughts. I'll pin the most thought-provoking response. This journey will challenge everything you think you know about astronomical observation. We'll meet the scientists who first recognized that space itself could act like a lens, explore the detective work required to separate real structures from gravitational mirages, and discover why some of our most important cosmic discoveries only became possible once we learned to embrace the universe's deceptions. The implications extend far beyond astronomy. In an age where we increasingly rely on remote sensing and indirect observation to understand everything from climate change to quantum mechanics, the lessons of gravitational lensing offer crucial insights into the nature of knowledge itself. How do we know what we know? How do we separate signal from noise when the medium itself is part of the message? Now let us begin our exploration of the universe's greatest magic trick and the brilliant methods astronomers developed to see through the illusion. Chapter 1. Cosmic Deception. The first hint that space might be playing tricks on us came not from a telescope, but from a solar eclipse. On May 29, 1919, British astronomer Arthur Eddington traveled to the island of Principe off the coast of Africa, carrying photographic plates and a desperate hope that Einstein's wild theories about curved spacetime might actually be true. What Eddington observed during those precious minutes of totality would fundamentally change how we understand observation itself. Stars that should have been hidden behind the sun were clearly visible, their light somehow bending around our star's massive gravitational field. The measurements were crude by today's standards, just 1.75 arcseconds of deflection, but they proved something profound. Light doesn't travel in straight lines through space. Space itself determines the path that light follows. This wasn't merely a confirmation of Einstein's theory. It was the first evidence that everything we see in the universe is potentially distorted by invisible gravitational forces. But it would take decades before astronomers realized the full implications of what Eddington had discovered. The real breakthrough came in 1979, when astronomers Dennis Walsh, Bob Carswell, and Ray Wayman were studying what they thought were two separate quasars. These incredibly bright objects, designated Q0957 plus 561A and B, appeared remarkably similar in their spectral signatures, the unique fingerprint of light that identifies each cosmic object. The similarities were so precise that the team began to suspect something extraordinary. They weren't looking at two objects at all, but rather two images of the same quasar. The concept seemed impossible. How could a single object appear in two different locations in the sky? The answer lay in the space between Earth and that distant quasar, a space dominated by a massive galaxy cluster whose gravitational field was so intense it split the quasar's light into multiple paths. Some light traveled around one side of the cluster, some around the other, and both paths eventually reached our telescopes. We were seeing the same object twice, like a cosmic double exposure created by gravity itself. This discovery, confirmed through careful spectroscopic analysis over several months, marked the birth of gravitational lensing as an observational tool. But it also marked the beginning of a profound epistemological crisis in astronomy. If we could see the same object multiple times, how many other observations were similarly compromised? How could we trust any image from deep space? The problem became more apparent as telescope technology improved. The Hubble Space Telescope, launched in 1990, began revealing gravitational lensing effects that were previously invisible. Galaxy clusters like Abele 2218 showed hundreds of background galaxies stretched into elegant arcs, their shapes completely transformed by the cluster's gravitational field. What astronomers had initially thought were unusual curved galaxies were actually normal elliptical and spiral galaxies viewed through nature as own funhouse. Mirror. Dr. Roger Linz from the Kitt Peak National Observatory described the growing awareness among astronomers. We suddenly realized we'd been looking at a distorted universe all along, but we've been calling the distortions real. This was, on hyperbole systematic surveys, revealed that gravitational lensing effects were present in virtually every deep field observation. The mathematics of gravitational lensing revealed why these effects were so pervasive. Einstein's field equations demonstrate that any mass curves space-time proportionally to its density. In the vast distances between Earth and distant galaxies, light encounters countless massive objects, galaxy clusters containing trillions of stars, vast dark matter halos, supermassive black holes, even smaller-scale structures like individual galaxies and dark matter clumps. Each gravitational encounter leaves its mark on the light. A photon that began its journey as part of a perfectly circular galaxy image might be stretched into an arc by a galaxy cluster, then slightly sheared by a dark matter subhalo, then magnified by a foreground galaxy, all while being subjected to the subtle lensing effects of hundreds of smaller masses along its path. By the time that photon reaches our detector, its original trajectory has been modified dozens of times. The cumulative effect is staggering. Computer simulations by cosmologist Rachel Mandelbaum at Carnegie Mellon University show that the average photon from a galaxy at redshift z equals 2, about 10 billion light-years away, as its path deflected by approximately 2 to 3 arcseconds due to gravitational lensing. This might seem small, but it's equivalent to observing a galaxy from New York and having its apparent position shifted by the gravitational influence of objects in Los Angeles. Even more disturbing is the discovery of what astronomers call weak lensing, systematic distortions so subtle they can't be detected in individual galaxies, but become apparent only through statistical analysis of thousands of objects. Every galaxy we observe is slightly stretched, rotated, or magnified compared to its true appearance. The effect is typically only 1 to 2% per galaxy, but when multiplied across the millions of galaxies in a typical survey, it represents a fundamental contamination of astronomical data. Dr. Sarah Bridle from University College London, who leads major weak lensing surveys, puts it in stark terms. We are not observing the universe. We are observing the universe as filtered through the gravitational potential of all intervening matter. Every measurement we make is a measurement of both the source and the lens. This realization forced a complete reconceptualization of astronomical methodology. Traditional approaches assumed that images represented direct observations of cosmic objects. But gravitational lensing revealed that astronomical images are actually composite measurements, part intrinsic property of the source, part cumulative effect of everything between the source and observer. The challenge becomes even more complex when you consider that many of the most important astronomical observations involve the faintest, most distant objects in the universe, precisely those objects whose light has traveled through the most gravitational fields and accumulated the most distortions. The cosmic microwave background, which carries crucial information about the early universe, has been gravitationally lensed by every massive structure that formed over the past 13.8 billion years. Galaxy surveys aimed at understanding dark energy and the expansion of the universe are similarly compromised. The shapes and apparent brightnesses of distant galaxies, the primary data used to construct our cosmological models, are systematically altered by gravitational lensing. In some cases, galaxies appear up to 50 times brighter than their intrinsic luminosity due to lensing magnification. Perhaps most troubling is the discovery that gravitational lensing can create entirely false signals. Galaxy clusters can magnify background supernova to the point where they appear to be closer and brighter than they actually are, potentially skewing measurements of cosmic expansion. Dark matter substructures can create apparent galaxy clustering where none actually exists. Even the cosmic web, the large-scale structure of the universe, shows features that are partly real and partly gravitational artifacts. This isn't merely a technical problem that can be solved with better instruments. Gravitational lensing is a fundamental consequence of general relativity operating over cosmic distances. As long as we observe the universe from a single vantage point, Earth, we will always see it through the collective lens of all intervening matter. The implications extend beyond astronomy into the philosophy of scientific observation itself. Gravitational lensing represents a case where the medium fundamentally alters the message in ways that can't be easily separated. Unlike instrumental effects that can be calibrated out, or atmospheric distortions that can be corrected, gravitational lensing is woven into the fabric of space-time itself. Yet rather than rendering astronomical observation impossible, this crisis has led to some of the most sophisticated measurement techniques in science. The next phase of our story reveals how astronomers learned to read the language of gravitational distortion and discovered that the universe's deceptions could reveal truths about reality that no direct observation could ever uncover. Chapter 2. Einstein's Lens in 1936. A struggling physicist named Fritz Zwicky was studying the Coma cluster of galaxies when he noticed something that defied explanation. The galaxies in this cluster were moving far too fast. According to Newton's laws of gravity and the visible matter Zwicky could observe, these galaxies should have been flying apart long ago. Yet the cluster remained gravitationally bound, as stable as if it contained 10 times more matter than anyone could see. Zwicky proposed what seemed like science fiction. The cluster must be dominated by dark matter, invisible material that revealed itself only through its gravitational effects. But he also realized something equally profound. If this invisible matter really existed in such vast quantities, it would bend light from background sources just as dramatically as the visible galaxies. The universe, Zwicky suggested, was filled with natural gravitational lenses that could magnify distant objects far beyond the reach of any earthly telescope. The mathematics of Einstein's general relativity supported Zwicky's vision. When light from a distant source passes near a massive foreground object, space-time curvature acts like an optical lens, bending the light rays and potentially focusing them toward Earth. But unlike glass lenses that have fixed focal lengths, gravitational lenses have a unique property. They can magnify objects by factors of thousands or even tens of thousands. The principle is elegantly simple. Imagine light from a distant galaxy traveling toward Earth. If a massive galaxy cluster lies directly in the path, its gravitational field creates multiple paths for the light to follow, some bending around one side of the cluster, others around the opposite side. From Earth's perspective, we see multiple images of the same background galaxy, each following a different light path and therefore arriving at slightly different times. But the real magic happens when the alignment is nearly perfect. If the source, lens, and observer are precisely aligned, the gravitational focusing effect can magnify a background object by factors of 10, 100, or in extreme cases, over 50,000 times. This natural magnification allows astronomers to study objects that would otherwise be completely undetectable with any conceivable telescope technology. Dr. Claudia Scarlata from the University of Minnesota discovered this firsthand when studying the galaxy cluster, MACSJ 1149.5 plus 2223. Through gravitational lensing, this cluster revealed a galaxy that existed when the universe was only 500 million years old, long before the formation of the first stars should have been possible according to standard cosmological models. Without gravitational magnification, this galaxy would have been millions of times too faint to detect. The discovery process requires detective work that rivals the most sophisticated forensic investigations. When astronomers observe a gravitational lens system, they see a complex pattern of distorted images that must be decoded to reveal the true properties of the background source. Multiple images of the same galaxy appear at different locations, each with slightly different magnifications and time delays. The time delays are particularly crucial, since different light paths around a gravitational lens have different lengths. Light following the shorter path arrives at Earth before light following the longer path. For the famous Einstein cross-lens system, the 4 images of the same background quasar show time delays ranging from days to months. By carefully monitoring these delays, astronomers can measure the expansion rate of the universe with unprecedented precision. Professor Sherry Sue's team at the Max Planck Institute has used gravitational lensing time delays to measure the Hubble constant, the rate of cosmic expansion, with accuracy approaching 1%. This measurement technique is completely independent of traditional methods using supernova or stellar populations, providing a crucial cross-check of our understanding of cosmic evolution. But perhaps the most remarkable aspect of gravitational lensing is its ability to map invisible matter with extraordinary detail. Dark matter, which comprises 85% of all matter in the universe, cannot be observed directly because it doesn't interact with light. Yet gravitational lensing reveals dark matter's presence and distribution through its effects on background light sources. The technique works through careful measurement of galaxy shapes in lensed images. Dark matter halos around galaxy clusters create systematic distortions that stretch background galaxies in preferred directions. By analyzing the shapes of thousands of background galaxies, astronomers can reconstruct detailed maps of dark matter distribution with resolution comparable to the best optical images. The Dark Energy Survey, led by Dr. Josh Freeman at Fermilab, has used weak gravitational lensing to map dark matter across 1/8 of the entire sky. The resulting maps reveal dark matter structures extending across hundreds of millions of light years, forming a cosmic web that guides the formation and evolution of all visible matter in the universe. These dark matter maps have yielded shocking discoveries. In 2007, the Hubble Space Telescope observed the galaxy cluster 1E06575558, known as the Bullet Cluster, where 2 galaxy clusters had collided at speeds exceeding 10 million kilometers per hour. While the visible matter in both clusters showed signs of violent interaction, gravitational lensing revealed that the dark matter halos had passed through each other almost unaffected. This observation provided the clearest evidence to date that dark matter is real and distinct from ordinary matter. The collision separated dark matter from normal matter in a way that could be directly observed through gravitational lensing, effectively proving that the universe contains vast amounts of material that interacts only gravitationally. Dr. Douglas Clough from the University of Arizona, who led the Bullet Cluster study, describes the impact. For the first time, we could see dark matter separated from everything else. It was like watching the invisible become visible through the bending of light. The precision of modern gravitational lensing measurements has reached extraordinary levels. The Hubble Space Telescope can detect shape distortions as small as 0.1% in individual galaxies. Ground-based surveys like the Vera Rubin Observatory will soon measure weak lensing effects for over 1 billion galaxies, creating the most detailed map of matter distribution in the universe. This precision comes from sophisticated analysis techniques that account for every possible source of systematic error. Atmospheric turbulence, instrumental effects, galaxy intrinsic orientations, and photographic noise must all be carefully modeled and removed to reveal the subtle gravitational lensing signal. The statistical methods required are among the most advanced in all of science, involving Bayesian inference, machine learning, and complex error propagation across millions of measurements. Modern gravitational lensing analysis also relies on advanced computer simulations that model the entire light path from source to observer. These simulations, run on supercomputers at facilities like the National Center for Supercomputing Applications, trace the trajectories of billions of light rays through realistic models of cosmic structure formation. The simulations reveal that gravitational lensing effects are far more complex than early models suggested. Light from a single distant galaxy can be lensed simultaneously by multiple foreground objects, creating intricate patterns of magnification and distortion. In some cases, the lensing effects of individual stars within foreground galaxies can be detected, a phenomenon called microlensing that allows astronomers to study stellar populations in galaxies billions of light years away. Perhaps most remarkably, gravitational lensing has enabled the detection of planets around stars in other galaxies. When a planet orbits a star that's acting as a gravitational lens, the planet's gravitational field creates brief spikes in the magnification of background sources. These microlensing events last only hours or days, but they provide the only known method for detecting planets and galaxies beyond our own Milky Way. The technological requirements for gravitational lensing research push the boundaries of astronomical instrumentation. The James Webb Space Telescope's unprecedented infrared sensitivity has revealed gravitational lensing effects in galaxies so distant their light has been traveling for over 13 billion years. At these distances, gravitational lensing is often the only way to study galaxy formation in the early universe. Yet for all its power, gravitational lensing remains fundamentally limited by the same problem that makes it necessary. We can only observe the universe from our single vantage point on Earth. We cannot move our telescopes to different locations in space to triangulate the true positions and properties of lensed objects. Every gravitational lens measurement requires sophisticated modeling and statistical inference to separate the intrinsic properties of sources from the effects of intervening matter. This limitation leads us to one of the most profound questions in observational science. When we can never observe an object directly, but only through the filter of gravitational fields, how do we know what's real and what's an artifact of our measurement process? The answer requires understanding not just the physics of light and gravity, but the epistemological foundations of scientific knowledge itself. Chapter 3: Impossible Precision. In 2011, astronomers made a discovery that seemed to violate the laws of physics. Using gravitational lensing to study a distant galaxy cluster called MAX J 0717.5+3745, they found that they could measure the position of dark matter within the cluster to an accuracy of just 50,000 light-years, despite the fact that the cluster itself spans over 5 million light-years and lies 5.4 billion light-years away. To put this in perspective, imagine trying to locate a specific building in Tokyo while standing on the moon, using only the shadow it casts. The precision achieved through gravitational lensing analysis exceeds what should be theoretically possible given the limitations of our telescopes and the fundamental quantum uncertainty in photon detection. Dr. Massimo Maghetti from the INAF Observatory of Trieste leads the team responsible for these measurements. We are achieving sub-percent accuracy in mapping mass distribution across cosmic scales, he explains. The precision is so high that we can detect dark matter substructures that contain less mass than our own Milky Way galaxy, even when they're billions of light-years away. This impossible precision emerges from a phenomenon that statisticians call ensemble averaging. While individual galaxy distortions due to gravitational lensing are subtle and difficult to measure accurately, the systematic distortion of thousands of background galaxies creates a signal that can be extracted with extraordinary precision through careful statistical analysis. The technique resembles the methods used in particle physics experiments, where individual particle interactions are too random to provide useful information. But millions of interactions reveal precise patterns that expose fundamental physical laws. In gravitational lensing, astronomers analyze the shapes of 100,000 or more background galaxies simultaneously, using Bayesian inference techniques to extract dark matter maps with resolution that approaches the theoretical limits of information theory. The mathematical foundation for this precision lies in the weak lensing power spectrum, a statistical description of how gravitational distortions vary across different angular scales. Dr. Catherine Hamans from the University of Edinburgh, who developed many of the statistical techniques used in modern lensing surveys, describes it as reading the collective whisper of gravity across cosmic time. Each background galaxy's shape carries information, not just about the dark matter directly in front of it, but about the entire three-dimensional distribution of matter along the line of sight. When astronomers combine shape measurements from galaxies at different distances, they can reconstruct the evolution of cosmic structure over billions of years with temporal resolution measured in tens of millions of years. This temporal precision has revealed fundamental surprises about how the universe evolved. The Dark Energy Survey's analysis of weak lensing data from 26 million galaxies shows that dark matter clustering grew more slowly than predicted by standard cosmological models. The discrepancy is small, only about 8%, but it is measured with such high precision that it represents a potential crisis for our understanding of cosmic evolution. Professor Elizabeth Croce from the University of Arizona, who led this analysis, emphasizes the significance. When you can measure cosmic structure growth to better than 1% accuracy, small discrepancies become major puzzles. We're either missing something fundamental about dark matter, or our models of cosmic evolution need major revision. The precision extends beyond dark matter, mapping to measurements of cosmic expansion itself. Gravitational lensing time delays, the different arrival times of light following different paths around a massive lens, can be measured to accuracies of hours even for light that has been traveling for billions of years. The most precise measurements come from the lens system known as PG 1115+080, where Dr. Tommaso Tru's team at UCLA has monitored 4 images of the same distant quasar for over 2 decades. The time delays between these images, ranging from 9 to 23 days, have been measured with uncertainties of less than 1%. This precision allows determination of the Hubble constant, the rate of cosmic expansion, with accuracy that rivals any other cosmological measurement technique. But the real breakthrough in precision comes from understanding and correcting systematic errors that initially seemed insurmountable. Gravitational lensing measurements are contaminated by dozens of different effects: atmospheric turbulence, telescope optics, detector response, galaxy intrinsic orientations, photographic noise, and even the gravitational effects of objects in our own solar system. Dr. Gary Bernstein from the University of Pennsylvania has spent decades developing techniques to account for these systematic effects. His team's approach involves creating mock galaxy surveys using supercomputer simulations that include every known source of error. By processing the mock data through identical analysis pipelines used for real observations, they can identify and correct biases that would otherwise contaminate lensing measurements. The level of systematic control required is extraordinary. For the Vera Rubin Observatory's Legacy Survey of Space and Time, astronomers must control instrumental systematic effects to better than 0.01% to achieve their scientific goals. This requires understanding how atmospheric turbulence affects star images, how telescope mirrors deform under gravitational stress, how detector pixels respond to different wavelengths of light, and how all these effects combine to create spurious galaxy shape measurements. Professor Rachel Mandelbaum from Princeton University, who leads systematic error research for several major lensing surveys, describes the challenge. We remeasuring effects that are smaller than any instrumental systematic we know how to control. It is like trying to measure the thickness of a human hair using a ruler marked in centimeters. The solution involves techniques borrowed from quantum error correction and signal processing theory. Multiple independent measurements of the same lensing effects are combined using maximum likelihood estimators that optimally weight different observations based on their expected error characteristics. Systematic effects that would overwhelm individual measurements become negligible when averaged across millions of independent observations. Machine learning techniques have revolutionized this precision measurement process. Convolutional neural networks trained on simulated galaxy images can measure gravitational lensing shape, distortions with accuracy that exceeds traditional analysis methods by factors of 2 to 3. These networks learn to recognize subtle patterns in galaxy morphology that human astronomers never noticed, extracting gravitational lensing signals from data that previously seemed too noisy to analyze. Dr. François Lanoussi from the French National Center for Scientific Research leads efforts to apply deep learning to gravitational lensing analysis. His team's neural networks can process galaxy shape measurements from millions of objects in minutes rather than months, while achieving precision that approaches theoretical limits set by photon counting statistics. The computational requirements for this precision are staggering. Modern weak lensing surveys generate petabytes of data that must be processed through analysis pipelines running on supercomputers with thousands of processors. The Vera-Rubin Observatory alone will generate 20 terabytes of data every night for 10 years, requiring computational resources comparable to those used for climate modeling or nuclear weapon design. Yet even these extraordinary computational efforts cannot overcome the fundamental limitation of gravitational lensing measurements, the degeneracy between different possible mass distributions that could produce identical lensing effects. Multiple dark matter configurations can create indistinguishable gravitational distortions, a mathematical phenomenon known as the mass sheet degeneracy. Breaking this degeneracy requires combining gravitational lensing with completely independent measurement techniques. Galaxy dynamics, X-ray observations of hot gas, and gravitational wave detections all provide complementary information about mass distribution that can resolve ambiguities in lensing analysis. The Laser Interferometer Gravitational Wave Observatory, LIGO, has opened an entirely new approach to this problem. When massive objects like black holes merge, they create gravitational waves that carry information about mass and distance completely independent of electromagnetic radiation. Combined with gravitational lensing measurements of the same systems, these observations provide unprecedented constraints on cosmic structure. Dr. Maya Fishbach from Northwestern University, who studies gravitational wave cosmology, explains the synergy. Gravitational waves tell us about mass in motion, while gravitational lensing tells us about mass at rest. Together, they give us a complete picture of how matter behaves across cosmic scales. The precision achieved through these combined techniques approaches limits set by fundamental physics rather than instrumental capabilities. Quantum mechanical uncertainty in photon detection creates irreducible noise in any optical measurement, while general relativistic effects introduce subtle correlations that must be modeled at the level of individual particle interactions. Yet astronomers continue pushing toward even higher precision through techniques that seem to border on science fiction. Proposals for space-based gravitational wave interferometers, like the Laser Interferometer Space Antenna, LISA, would enable gravitational lensing measurements of massive black holes across cosmic time, providing precision tests of general relativity in the strong field regime. Even more ambitious are proposals for using the Sun itself as a gravitational lens. At distances beyond 550 times Earth's orbit from the Sun, our star's gravitational field could focus light from distant objects with magnifications exceeding 1 billion. Such observations would require spacecraft missions lasting decades, but could potentially resolve features on exoplanet surfaces or map dark matter substructure with unprecedented detail. This relentless pursuit of precision reflects a deeper truth about gravitational lensing. It represents our most powerful tool for studying the universe precisely because it exploits the fundamental geometry of space-time itself. Unlike any human-made instrument, gravitational lenses improve with distance. The farther away an object is, the more intervening matter can focus its light and reveal its properties. Chapter 4. Dark Revelations on March 4, 2006. Astronomers pointing the Hubble Space Telescope toward a seemingly empty patch of sky made a discovery that would fundamentally challenge our understanding of reality itself. The patch, designated Cosmos Field, appeared to contain nothing but scattered points of light. But when Dr. Richard Massey's team at Caltech applied gravitational lensing analysis to the image, they revealed something invisible and terrifying: vast filaments of dark matter spanning hundreds of millions of light-years, forming a cosmic web that dwarfs all visible matter in the universe. The dark matter map created from this observation was unprecedented in its detail and scope. Using the distorted shapes of over 575,000 background galaxies, the team reconstructed the three-dimensional distribution of dark matter across cosmic time, revealing structures that no direct observation could ever detect. What they found challenged every assumption about the nature of matter and the structure of reality. The cosmic web revealed by gravitational lensing shows a universe dominated by invisible architecture. Dark matter filaments, some containing more mass than 1 trillion suns, connect galaxy clusters across distances that span significant fractions of the observable universe. These filaments act as highways along which ordinary matter flows, determining where galaxies form and how they evolve over billions of years. Dr. Jason Rhodes from NASA's Jet Propulsion Laboratory, who contributed to this dark matter mapping effort, describes the implications. We discovered that everything we can see, all the stars, galaxies, and gas clouds, represents less than 15% of the matter in the universe. The remaining 85% is completely invisible, detectable only through its gravitational effects on light. But gravitational lensing revealed something even more disturbing about dark matter. It doesn't behave like any known form of matter. While ordinary matter interacts electromagnetically, creating friction and heating during cosmic collisions, dark matter appears to be effectively collisionless. When galaxy clusters merge at velocities exceeding 4,000 kilometers per second, dark matter halos pass through each other like ghosts. This ghost-like behavior was most dramatically demonstrated in the galaxy cluster 1EO 657558, known as the Bullet Cluster. When the Hubble Space Telescope observed this system through gravitational lensing, it revealed that the dark matter had separated from the ordinary matter during a violent collision between two galaxy clusters. The ordinary matter, visible as hot X-ray emitting gas, remained at the collision site due to electromagnetic interactions. But the dark matter, revealed only through its gravitational lensing effects, had continued moving as if the collision never happened. Professor Doug Clough from the University of Arizona, who led the Bullet Cluster analysis, puts this in stark perspective. Dark matter interacts so weakly with itself that galaxy clusters containing 10 trillion solar masses can pass through each other with less friction than air molecules colliding in Earth's atmosphere. The implications extend far beyond astronomy. If dark matter comprises 85% of all matter but interacts only gravitationally, then our entire understanding of fundamental physics is incomplete. Every particle physics experiment, every quantum mechanical theory, every chemical reaction we've ever studied involves only the 15% of matter that happens to interact electromagnetically. Gravitational lensing studies have revealed even more disturbing properties of dark matter. Unlike ordinary matter, which concentrates in stars and planets with well-defined boundaries, dark matter appears to exist in vast, diffuse halos that extend far beyond visible galaxies. These halos can contain 100 times more mass than all the stars in their central galaxies combined. The Hubble Space Telescope as Cosmic Evolution Survey, COSMOS, used weak gravitational lensing to map dark matter around 10,000 galaxies across a volume of space containing over 1 billion cubic light-years. The results showed that every galaxy exists within a dark matter halo, and that these halos merge and interact according to laws that we're only beginning to understand. Dr. Nick Scoville from Caltech, who leads the COSMOS survey, describes the revelation. Galaxies are just the luminous tips of dark matter icebergs. The real mass distribution of the universe is completely invisible to direct observation. We're living in a universe made primarily of something we can't see, touch, or detect except through gravitational lensing. The precision of modern dark matter mapping has revealed structures that challenge theoretical predictions. Gravitational lensing observations of galaxy cluster Abell 520, dubbed a train wreck cluster, show a massive dark matter concentration that exists without any associated galaxies. A dark core that contains more matter than our entire local group of galaxies, but produces no visible light whatsoever. This discovery violates predictions of cold dark matter theory, which suggests that dark matter should always be associated with ordinary matter. The existence of dark cores implies that dark matter can be stripped away from galaxies during cluster mergers, accumulating in regions of space that contain no stars, gas, or any form of detectable matter except for the gravitational distortions they create. Professor Andisha Madhavi from San Francisco State University, who discovered the dark core phenomenon, emphasizes its significance. We found dark matter existing in complete isolation from ordinary matter. This suggests that the relationship between dark and ordinary matter is more complex than any current theory predicts. Gravitational lensing has also revealed the evolution of dark matter structure across cosmic time. By analyzing background galaxies at different distances, astronomers can reconstruct how dark matter clustering has changed over the past 10 billion years. The results show that dark matter structure grows through hierarchical merging. Smaller halos combine to form larger ones in a process that continues to the present day. But the growth rate measured through gravitational lensing doesn't match predictions from cosmic microwave background observations. This sigma-8 tension, named after the statistical parameter that describes matter clustering strength, represents a potential crisis for cosmological models. Either our understanding of dark matter physics is incomplete, or the standard model of cosmology needs fundamental revision. The Dark Energy Survey, which used gravitational lensing to map dark matter across 5,000 square degrees of sky, found that matter clustering is weaker than predicted by about 8%. While this seems small, the measurement precision is better than 1%, making the discrepancy statistically significant at the level that typically indicates new physics. Dr. Elizabeth Krause from the University of Arizona, who led this analysis, describes the implications. When precision measurements disagree with theoretical predictions, it usually means we're missing something fundamental. The question is whether we're missing something about dark matter itself or about how gravity works on cosmic scales. Recent gravitational lensing observations have revealed even stranger aspects of dark matter behavior. Ultra-diffuse galaxies, objects as large as the Milky Way, but containing only 1% as many stars, appear to exist within dark matter halos that are either much larger or much smaller than theoretical predictions suggest. Some ultra-diffuse galaxies seem to contain almost no dark matter at all, while others are dominated by dark matter to an extreme degree. The galaxy NGC 1052DF2, discovered through careful gravitational lensing analysis, appears to contain less than 1/400th the dark matter that theories predict. If confirmed, this observation suggests that dark matter and ordinary matter can be separated more easily than previously thought, potentially providing clues about dark matter's fundamental nature. Professor Peter Van Dokkum from Yale University, who studies ultra-diffuse galaxies, explains the puzzle. We thought dark matter and ordinary matter were inseparably linked during galaxy formation. But gravitational lensing shows us galaxies that seem to have lost their dark matter entirely. This challenges our most basic assumptions about how structure forms in the universe. Advanced gravitational lensing techniques are now probing dark matter structure on scales approaching individual stars. Observations of strongly lensed quasars show brightness fluctuations that can only be explained by dark matter substructures with masses similar to dwarf galaxies passing through the light paths. These subhalo detections provide the first direct evidence for dark matter clustering on small scales. The implications reach into particle physics itself. If dark matter consists of unknown particles, their mass and interaction strength must be consistent with the clustering patterns observed through gravitational lensing. Current observations suggest dark matter particles must be lighter than initially predicted by supersymmetric theories, potentially ruling out entire classes of candidate particles. Dr. Yashar Hezaveh from Stanford University, who uses machine learning to analyze gravitational lensing data, summarizes the current understanding. Gravitational lensing has revealed a universe where the majority of matter is invisible, behaves unlike anything in our experience, and follows laws we don't yet understand. We're essentially doing archaeology on the invisible universe. Perhaps most profoundly, gravitational lensing observations suggest that dark matter might not be uniform throughout space. Recent analyses of the cosmic microwave background lensing by the Planck satellite indicate that dark matter density varies significantly across different regions of the observable universe. If true, this would violate the cosmological principle, the assumption that the universe is fundamentally homogeneous on large scales. These revelations force us to confront an uncomfortable reality. We live in a universe where 85% of all matter remains completely mysterious. Gravitational lensing, our primary tool for studying dark matter, can map its distribution and evolution, but cannot reveal its fundamental nature. We can see its gravitational fingerprints across billions of light years, but we have no idea what dark matter actually is. This ignorance extends to dark energy, which comprises an additional 68% of the universe's total content. Combined with dark matter, these invisible components mean that 95% of reality consists of phenomena we don't understand. Gravitational lensing has revealed the scope of our ignorance with unprecedented clarity, showing us a cosmos dominated by invisible forces and unknown physics. Chapter 5. Universal Mirrors. In the summer of 1988, astronomer Jacqueline Hewitt was analyzing radio telescope data from the Very Large Array in New Mexico when she discovered something that seemed to violate causality itself. She was observing a distant quasar designated MG 1131 plus 0456, tracking its brightness variations over several months. When she noticed an impossible pattern, the quasar appeared to brighten and fade in two different locations simultaneously, but the variations weren't quite synchronized. One image consistently brightened 13 days before the other. This observation revealed one of the most profound implications of gravitational lensing. When massive objects split light into multiple paths, they create natural time machines. The different paths have different lengths through curved spacetime, causing light following the shorter path to arrive days, months, or even years before light following the longer path. From Earth's perspective, we can watch the same cosmic event happen multiple times, separated by precisely calculable time delays. Dr. Chris Fasnacht from UC Davis, who studies gravitational lens time delays, explains the phenomenon. We're essentially watching the universe in slow-motion replay. A supernova explosion or quasar outburst sends light along multiple gravitational paths, and we receive these signals like echoes arriving at different times. It's as if the universe provides its own cosmic instant replay system. The implications for astronomy are staggering. When the Hubble Space Telescope observed the galaxy cluster Max J 1149.5 plus 2223. Gravitational lensing revealed a supernova explosion in a background galaxy that occurred when the universe was only 4.4 billion years old. But the lensing created 4 separate images of this explosion, with predicted time delays ranging from months to over a year. Astronomers could literally schedule observations to watch the same stellar death multiple times. Professor Patrick Kelly from the University of Minnesota, who discovered this Refstal supernova, describes the unprecedented opportunity. For the first time in astronomical history, we could predict exactly when and where a supernova would appear in the sky. The gravitational lens system acts like a cosmic forecast, telling us when light following different paths will reach Earth. But time delays represent just one aspect of how gravitational lenses transform our view of the universe. Perhaps even more remarkable is their ability to act as natural telescopes with magnifying powers that no human technology could ever achieve. While the largest ground-based telescopes have effective diameters of 30 to 40 meters, gravitational lenses can have effective diameters of millions or billions of light years. The magnification depends on precise alignment between source, lens, and observer. Dr. Dan Coe from the Space Telescope Science Institute has pioneered techniques for using galaxy clusters as gravitational telescopes. His team's analysis of the galaxy cluster MAX J 1149.5 plus 223 revealed the most distant galaxy known at the time of its discovery, existing when the universe was only 380 million years old. Without gravitational magnification, this galaxy would have been over 1,000 times too faint to detect. The discovery process requires extraordinary precision in modeling gravitational lens systems. Modern cluster lens models incorporate thousands of individual mass components, galaxy-scale dark matter halos, diffuse cluster dark matter, hot X-ray gas, and even stellar mass objects within individual galaxies. Computing the magnification map for a single cluster lens can require supercomputer simulations taking weeks to complete. Professor Adi Zitran from Ben-Gurion University, who creates these detailed lens models, describes the complexity. Each galaxy cluster contains hundreds of gravitational lenses operating simultaneously at different scales. We're essentially solving a cosmic jigsaw puzzle, where every piece is invisible and the final picture shows us objects that exist beyond the edge of observable space.